Mm. Good morning, everyone. Welcome to the ninth talk of the 10th edition of Alumni Research Talks organized by CSA. Today, we are hosting Dr. Ganesh Ananthanarayanan, who is currently working as a principal researcher in Microsoft's Azure for Operators group in the Greater Seattle area. Dr. Ganesh graduated from BITS Pilani with dual degree in civil engineering and computer science in 2005. He then joined Microsoft as a research fellow and worked there for 2 years. After that, he pursued his PhD at the AMP lab at UC Berkeley. He is also the recipient of the prestigious UC Berkeley Regents Fellowship. Mr. Ganesh joined Microsoft as a researcher after his PhD in 2013. He has published over 30 papers in systems and networking conferences, which have been recognized with the Best Paper Award at ACM SEC 2020, CSAW 2020, Applied Research Competition Award runner-up, and ACM Mobisis 2019 Best Demo Award. He has also the highest rated paper at ACM SEC 2018. Today he will educate us about democratizing video analytics, the quest for holy trinity of low latency, low cost, and high accuracy. So let us hear from him.
Thank you, Mohit. Can everyone hear me? Can you all see the screen?
You're audible.
Okay, great. Yeah, so I'll get going. Yeah. So yeah, hi. So again, thanks, Mohit, for the introduction. So today I'll be talking about video analytics systems, and specifically from the point of view of how there is this tussle between low latency, low cost, and still yet achieving high accuracy. But before I go there, just a quick question on the logistics. So like if somebody was to ask a question, I can't see it if someone raises their hand. So it would just be audio that I'll hear, right? Mohit? Okay, anyways, yeah.
Sir, you will be able to see in the right side. But we will be taking Q&A after your talk.
After the talk. Okay, got it. All right, cool. Okay, so this is joint work with a lot of people over the last couple of years, both researchers, interns, professors. And the motivation for why we started with this work was that there were cameras everywhere, cameras in restaurants, in retail stores, deployed by governments for, often traffic, smart cities purposes. And, there was a statistic that there is a camera for every 7 people in the US. And I'm sure the numbers are similar, in other parts of the world as well. And clearly video analytics and any kind of real-time actions that you take based on it is integral to the whole promise of 5G. So let me walk you through a couple of applications that are possible with something like this. And these are, applications that based on like pilots that we have collaborated with in a few cities. For instance, in the smart city scenario, when the work that we did with the city of Bellevue, another city in Australia, they wanted to use the traffic cameras to get car, bike, and pedestrian counts, and also understand when there is a near collision between between a vehicle and pedestrian or a bicycle, and often this is stuff that allows for the fact that they can deploy these traffic cameras for efficiency and safety. So let me play this video. I hope this video plays, that shows what could happen. So this is an example of an application that requires real-time live video analytics. It's not something you can do after the fact. Let me walk you through another application. skip this. It's with parking. Often in cities here, finding parking is, especially in dense cities, can be pretty stressful. With folks having to drive around a fair bit, and this only adds to the congestion anyway. So compared to the general approach where sensors are deployed at these individual parking slots to detect if that slot is occupied or not, an alternate approach that many parking lot owners actually would want is also the fact that they deploy cameras, and over there any kind of local network, these camera feeds are analyzed on an edge box closer to where the cameras are. The edge, in contrast to say the cloud, which is much farther from where the cameras are. And that can sort of like power a whole bunch of things around real-time parking dashboards. Even your maps can drive people or direct people to the nearest parking slot. And the application is fairly, straightforward in that objects, cars specifically, have to be detected. As you can see on the left, and then on the right, as you can see, these detections get converted into occupied or unoccupied statuses. Here, of course, the text of occupied and unoccupied might be pretty small, but this is another popular application. This is sort of like work we've been doing with Fujitsu, where where the parking application itself was integrated as part of Fujitsu's 5G stack with their edge and their radio access networks. So this just gives a flavor of the kind of applications that can be enabled by analyzing live video streams on cameras deployed, practically all over us. So our goal essentially was to democratize video analytics, because when we came from it, we saw that there was a lot of accuracy, a lot of excitement in what vision could do, but at the same time, it was very expensive. And so what we wanted to do was take these video analytics, the DNNs and the algorithms and so forth, make it low cost, and also at the same time ensure that we actually build a system that guarantees privacy for us as well. For folks that are interested, I would point you to this paper that we wrote a couple of years back on then calling out that, because of reasons for data volumes, compute demand, and latency, we actually believe in many ways edge computing and video analytics are a very good match, and that video analytics will be a killer app for edge computing. For folks that don't really know what, are very familiar with what edge computing is sort of like, relatively small compute boxes that you put closer to, where the camera feeds are. This can be in your building. This can be, like, say, in a hostel building to get the cameras in the building. This can be in a radio base station or somewhere that we don't have to go all the way to, say, an Azure data center or an AWS data center. Okay. So what's our video analytics stack looking like? It is clearly not targeted at a single application vertical, but a whole bunch of verticals around, mobility, retail, and so forth. And for all these applications, as I'll talk about it soon, the applications are expressed like a pipeline of sorts. And this pipeline optimizer essentially takes this pipeline and sort of like gets the best, implementation choices, so to speak. Very not too dissimilar to a SQL query optimizer. And once you get this optimized pipeline, then this is passed to a resource manager that executes it across the edge and the cloud in that continuum. And finally, I'll also cover how this live video analytics generates an index that can be used for querying videos after the fact. See, later on, going back to historical videos. So the talk, basically, I had three things planned. One was firstly talking about video analytics, how to do it with approximation. There is a part in between about how to actually do a certain operation called profiling that I'll cover. But I think in the interest of time today, I'll sort of like, either skip the second part altogether or maybe briefly go over it. And then I'll talk about the third part on querying on stored videos. Okay, so let's get to what this pipeline means, right? So video analytics applications often express what they want to do in a pipeline. Like for instance, in this example, this is an application where that says that, hey, alert me when a car crosses a certain line of interest, this red line as you see here. So the operators in this are that, the video frames, the video stream is essentially decoded into frames. And these individual frames are first, resized and, sampled out. And like, for instance, a 1280p video would just get to 480p, 30 FPS goes to 5 FPS. And then you run it through a background subtractor, this black box here. That doesn't know that it's a car or anything. It just knows that there's some moving object, some change happened. And then the background subtractor detects then it passes through a line occupancy analyzer that detects if this moving object that I just saw, was it over this line? And if it is over the line, then we run a light deep neural network, a machine learning model, in this case, say YOLO, that detects what kind of object it was. This model is designed to at least train for either on, say, the COCO dataset that has 80 classes, or the ImageNet dataset which has 1,000 classes. And these are public datasets and classes available. You can find it. So this one, for instance, says that this light model that, hey, I think it's a car, but I only have a confidence of 0.5 on a scale of 1. And so we say, okay, that's not good enough. And so then we pass it through a heavy DNN that has a much higher confidence. So as you can see in this, there are plenty of decisions that you have to make, what we call configurations. Like, what's the resolution that you have to resize to? What's the frame rate that you have to do for frame selection? What are the models that you want to use here? And there are plenty such configurations. And these configurations have an impact on the resource usage and the accuracy. Take, for example, these two simple configurations, frame rate and resolution. As you can see in these graphs, while the individual specific values aren't that important, what is important is the trend. In that there is a trend where, sure, with varying these configurations, both the quality or the accuracy and the resource usage, in this case, say the CPU usage, increases for this video analytics pipeline. Take, for instance, also beyond frame rate and resolution, say the deep neural net, the DNN that was used there. Using something like a single shot object detector, can work for certain videos if the video is not that cluttered. But at the same time, if the scene is very cluttered, like a busy downtown or something, then we need something more heavyweight like the YOLO model. So essentially these configurations, right? These various, knobs and so forth, how much do they differ? I mentioned these two axes, right? One is in terms of the accuracy, and accuracy being measured here as an F1 score, and the resource demand itself. As you can see on this graph, there is like a huge spread in terms of each of these x's here. The blue x's represent like an individual configuration, and we see that there is a huge spread of quality or accuracy and the CPU demand for these different configurations. Hence, picking them is pretty important in terms of how cost efficient your system is, how accurate it is, and so forth. Take these 2 points, for instance, that I've just arbitrarily pulled out. You can see that these 2 points have more or less the same accuracy, yet their resource demand is 2 orders of magnitude different here, between 1 and 100. So in this situation, for this query, if we had picked the point on the right, we would essentially be paying 100 times more cost to get the accuracy that you could have gotten with this point itself. And hence we would have left savings on the table. So this spread is a property that is generally prevalent in all video analytics pipelines, and it is important that we pick the right one so that we have a resource efficient system. And this spread exists for multiple such video analytics queries. And often this is data dependent. This is video dependent. It's dependent on the camera itself, what the lighting is, sometimes lighting, occlusions, object colors, all of this matter. And I know earlier in the talk, I drew an analogy with with the database queries, a SQL query optimizer. But the analogy doesn't fully carry over because, unlike SQL query operators that actually have, have actual analytical models that model this resource quality profiles, for video analytics, no such analytical models exist. So we have to build this model and make that selection. And on top of it, these video analytics pipelines often have to run in a hierarchy of clusters, as I said multiple times about edge compute boxes. Like for instance, there are cameras, some smart cameras have some amount of compute already on them. And then there is this edge clusters that could be running, as I said, say in a hostel building, say something on campus, say something in one of the FD buildings, wherever. And then there is a cloud. So our problem statement with all this background that I just covered is we need to pick these configurations, the knobs and implementations for these video pipelines, and we need to place the individual modules of that pipeline across this hierarchy of clusters that I just mentioned. And we have to do both of them jointly. More specifically, we need to decide the configurations and placement for a set of queries such that we maximize their aggregate accuracy or quality. This could be average, min-max, whatever it is. Yeah. And often these different video pipelines, right? They have diverse quality requirements. Not all of them need the same level of accuracy. Like for instance, if I'm just doing a license plate based tolling on a highway, then I do require very high accuracy. You don't want to bill someone else. But at the same time, if I'm just counting cars to say change traffic lights automatically, as we saw in that motivational example where traffic light was changed automatically, you don't need complete accuracy. Like you're probably going to change the traffic light, regardless of whether there are 10 cars or 8 cars. So, probably plus or minus 20%, okay, not a problem in the error. So the overview of a solution is as follows. There are video pipelines. So first we pass this video pipeline through a profiler. Remember that I said there are no analytical models available, unlike SQL queries for these pipelines. So we need to profile them to get these resource quality profiles. And then we pass this minimum quality, I just covered this diverse quality requirements. We take both of them and pass it through the scheduler, which then goes ahead and decides the specific configurations and places them across this hierarchy of clusters. So the solution has two main components. One is efficient profiling of these resource quality relationship, and the second is an actual scheduler that decides the configurations and the placement. Okay. So let's go over this one by one. So the profiler first, right? So the profiler's job essentially is to take a configuration and for each configuration convert it into get both the resource and the quality. And the way we do it is that we take a sample representative sample video set, and for this sample video set, say this could be, say you're running this query, say you're going to run this query 24/7. So you could take, like, say, a few minutes or a few tens of minutes of video and then run through all the configurations on this resource, on this sample video to get the resource requirement and the accuracy. But which gets to the question, accuracy as relative to what? Because unlike unlike in the lab, in real world there is no labeled data set that is available. So what we do is take this thing called a golden configuration. This is often the configuration that is the most expensive, like the highest resolution, no frames are dropped, and the most expensive, say, neural network that you can get for an object detector, say. And then with this, we do a pretty targeted search for just the promising configurations. So on this two-dimensional, axis of the quality and the resource demand, what we do is essentially pick a few initial configurations and then run them on the entire data set. And then based on the results that comes out, what we do is we take a few subset of those configurations and only probe them further, because this is to ensure that the profiling itself doesn't become too expensive. And some of it will be covered in that second part of the talk that I said I would sort of like go through briefly. But based on this, what we do is clearly, to the left is more efficient, to the right at the top is higher quality. But this is a lot of points for the scheduler in the next stage to take in. So what we do is this following key thing. Look at these 2 points, the green and the red, right? The red is strictly better than the green in both the accuracy of the quality and its resource demand, which means that there is no reason why you would, if the red exists, that you would ever pick the green, because the green isn't beating the red on any dimension, in which case it is not even useful anymore. So if you look at the boundary of these points, that is called Pareto optimality. And so what we do is generate what is called a Pareto boundary of optimal configurations. A Pareto configuration or a point is such that any configuration that's not on the Pareto boundary, like a non-Pareto plan anywhere else here, will not beat this Pareto configurations in both quality and resources. And this is very handy because this is a big reduction in the search space for the scheduler that will come up next. From getting in from hundreds of configurations, now it just has a few handful of configurations it has to consider for its scheduling. And remember, the scheduler's job is to pick the right configuration, good, and also schedule the different modules on this hierarchy of clusters. Okay. And this hierarchy, needless to say, consists of compute at these individual locations and network connecting them. So what we do to, sort of like have this deal with this multi-resource problem of the compute and the network is to define something called a dominant resource demand. So essentially what we do is the following, which is that for each, configuration and a possible placement that you can have, right? Like for instance, in that earlier pipeline, you could probably schedule this background subtractor and this line overlap analyzer on, say, right on the camera or right next to the camera. Perhaps the light DNN can be somewhere in between and the heavy DNN can run in the cloud. Now, this is one possible placement option that you have. So what we do is for each configuration placement pair, we see like, oh, okay, so what's the fraction of the resource it uses at each location? And then we take the maximum of this fraction. Note the subtle point here in that by doing this maximum, we've actually made the resource demand dimensionless. Earlier, compute was in cycles, network was in bits per second, megabits per second, memory was in megabytes or gigabytes. But by taking this fraction and taking the maximum of it, we've essentially squared the problem around the apples and the oranges here, in that everything is dimensionless and it's just the dominant resource demand. And the fact that it's dimensionless means that it can extend to multiple resource types. And also, I'll refer to you to the paper for more details, is that this dominant resource demand actually avoids the lopsided, sort of like excessive drain of any single resource at a location. Okay. So now that for each configuration placement pair, we have one dominant fraction, right? And we have this for every single query and so forth. So the scheduling heuristic goes as follows. It's a greedy heuristic, so there's no algorithmic guarantees here, and it's an open problem. How do you solve this in an algorithmic sense? And this is of big interest to us right now as well in the Azure for Operators group. But the heuristic that we have as yet is as follows. As we said, we have the dominant demands. Allocate this demand in very small increments, because the problem itself is pretty hard. It's NP hard. So allocate the demand potentially in small increments and then see which one, for this additional increment of resource that you provides you the most amount of improvement in accuracy. Clearly, for folks that are algorithmically minded, you will clearly sense that, look, this is a greedy approach, so it is bound to get stuck in local maxima. And that is true. That is true. It's just that this is a heuristic that works well in practice, but sufficient room for improvement on this. In terms of evaluation highlights on this, we tested with videos from traffic cameras, surveillance cameras. The original video frame rates were this, and the resolutions were this. And generally, what we saw was that compared to competing baselines, our system is considerably more accurate. And even though we have a heuristic that I said, can get stuck in local maxima and so forth, in practice, it turns out to be, pretty close to what the optimal solution would be. We also tested for the scalability of the system and ensured that, even if there were some errors in the profile, the resource accuracy profile, we can adapt to the errors as well. Lots of details that I did not fully cover in this part of the talk, but I encourage you to look actually at the paper that actually lists a lot of the details in there. So this covers the first part of the talk. And as I said, let me quickly go over the second part of the talk, which addresses the problem of that profiler. Remember that the profiler, I said, was expensive because the configuration space is huge. And so we don't want to search everything. So, perhaps some kind of greedy search would help and so forth. But this one is a clever technique to ensure that we can dramatically reduce the profiling cost. So, clearly the current solution that I just described is something where it picks the best configuration by just profiling once at the beginning. That's it. It records using some sample videos, as I said, a few tens of minutes and so forth. But the best configuration actually changes a lot. And take this example here, right? If you take the example here, there's two, this is for, say, the frame rate alone. And this is the axis. On the x-axis is the F1 score. The y-axis, note that the time is just in a matter of a few seconds. So look at the first video here where nothing is moving, right? If you look at these two curves, high frame rate and low frame rate, you would see that more or less they are overlapping with each other, so much so you can't even spot the blue line much, right? Because cars aren't moving, so it doesn't matter what frame rate you're running it at. But on the video on the right, as cars start moving, note these two curves diverge. You see that now? There's a significant difference in accuracy, often, as you would see. More than 30% drop in accuracy. And so this kind of gets to the point where, not only is the best configuration video dependent, the video content itself changes over time. Hence, the best configuration also varies over time. So instead of the approach where we customize the video pipeline just to the video content, what we need to do is adapt it as the video dynamically changes. And there is a lot of value to doing it, and I'll show you a quantification of this. Take this graph itself. On the y-axis is resources, okay? So lower is better. On the x-axis is accuracy. So clearly, more to the right, better. Look at these two comparative things around a one-time update and something that does a periodic update, right? This is one-time profiling, so to speak. So one-time profiling is the accuracy is a little bit over the place, but it doesn't find, it doesn't find something with the best resources, because by periodically changing it, we see that we can find something, the configurations that are much better in their resource consumption. We saw that example with frame rate, where instead of running it on a high frame rate throughout, if we know that cars aren't moving, and at those times say we're running at a low frame rate, then that saves us on processing resources, right? But this graph here is a little bit of a cheating. because I've showed that, okay, it's great if you periodically profile, you can get great configurations. But if you include the profiling cost, then it becomes a problem, because then we're essentially getting to a point where the profiling cost itself is so high that any savings that you get out of one-time profiling all vanishes. So this is kind of the problem with profiling itself. So this part of the talk that I will not fully go through in depth is just about the fact as to how do you reduce this profiling cost. Very much aligned with the earlier part of the talk that wanted to run this, this queries across, all this hierarchy, pick the configuration and so forth. And picking the configuration required profiling, but profiling is expensive. And at a high level, we have 3 key techniques to profile it, which is that how often do you profile it? So there is a lot of temporal correlation in these videos. You don't have to profile it every second or something. And temporal correlations also mean that certain configurations, once they're bad, they usually tend to be bad. So that is one thing that we use. A spatial correlation is a key technique that we use here, because spatial correlation says that, hey, you know what, cameras that are all deployed, say, in the same city, right? They all more or less tend to have the same kind of lighting and so forth in the city. So, you can actually use that as a fact where if you profile for one of those cameras, you can use the same result for all the cameras in this. So that, if you have 10 cameras and you profile only once, automatically you get a profile, a savings in cost of 10x. The third is that, well, the space itself is a combinatorial one. Typically what we've seen is that, there is a certain level of independence of these configurations. So you can sort of like convert this otherwise combinatorial space into sort of like a more linear, search space. So as I said, I'll skip through the details of this in the interest of time. But please feel to check out the paper, and happy to cover any questions that you would have. Let me get to the third part of the work I wanted to cover, which was about we've talked about live video analytics so far. The third part of the work is interactive querying of these stored video data sets. Sorry, I'm just having a little bit of a PowerPoint issue. Should be back. You guys can still see my screen, right? Yes, I hope so. Yeah, okay. So there's a massive amount of, recordings of video happening everywhere, on the highways, at home, and essentially people do this recording to find this thing where, find me all the trucks in, say, Bellevue videos, say, for instance, Bellevue is a city, yesterday. Find me all the red cars, a whole bunch of stuff. And the way this happens is, okay, so these frames are taken, object detectors are run, and then we find like ones that have cars and so forth. Now, this is a very slow process, and it's a costly process. If I'm coming right now and saying, hey, find me the things that have, it's like any query that you want to write. I am not exactly signing up to sit for hours for you to get back with the result. And so, this is pretty slow and costly. So one option is, don't start the processing while I'm asking you for the result. Do it at ingest time on those live videos as they're coming in, keep processing them. Yeah, sure. Then you'll have the results available on the spot. So you can just go ahead and do it. But the thing here is that if you ingest all the videos for the results, that's pretty costly and also wasteful, because as we all know, most videos never get looked at. They're just recorded. They're there till for like an expiry time and they just delete it. So if you analyze all these videos at ingest time, it gets to a pretty pricey, point in terms of how much it costs to do this indexing. At the same time, we just saw that if you just do nothing at ingest time and only do everything at query time, and I'm just asking you for the question, then that takes a lot of time as well. Like for instance, on a month-long video, it can take 5 hours. So if I just come and say, hey, find me all the cards in this video set, in the last month, I'm going to sit for a long time before I get some results. 5 hours is hardly interactive. So our job, our goal is to enable low latency and low cost querying over these large historical video data sets. So if you look at this two-dimensional axis around query latency, which is how long it takes for the query to come back, and the ingest cost, how much cost does it take? What we see is the following, that clearly we want to get low, and where it is that if you have something, those two extremes that I mentioned, an ingest heavy option, that falls somewhere here. The ingest cost is pretty high, but the query latency is low because you just have to do a simple lookup at query time. The other hand, if you do a query heavy thing where you do all the work at query time, you don't really have much of an ingest cost. But so there's no wastage on the cost, but the query latency is very high. Our goal naturally is to be there. Okay? And we get there using three sort of like intuitive techniques. One is have a low cost indexing mechanism at ingest time. The second is sort of like remove, despite the fact that it's a low cost indexing, so there is some amount of junk that we end up indexing, remove that all at query time quickly to provide high accuracy and sort of like enable trade-offs between the two. So I'll cover the first two parts of it. So, at ingest time, sure, we can process the video frames. Our cost was shooting up because we were running a very heavy duty DNN, right? And that CNN that you see here is not a typo, it's just a kind of DNN, which is a convolutional neural network. So you, instead of using a very heavy duty, expensive DNN, you can use something very cheap. What are called compressed DNNs or specialized DNNs. They're like lots of layers stripped out and all that. So, that's great. So then what you can do is, as the frames come in, instead of running this expensive CNN and producing the index, just run a very simple specialized CNN. That is very inexpensive, or relatively. But the cheap CNNs are less expensive for a reason. That's because they are also less accurate than the expensive CNN. Like for instance, if you take a certain classifier, and classifiers typically produce this list of probabilities. Early in the talk, if you recall, I told you about MS COCO dataset or ImageNet dataset that have like 1,000 classes. If you give an image, the classifier is basically saying, hey, with a probability of 0.8, I think it's a truck. With a probability of 0.05, I think it's a dog, and so forth. And all these probabilities, of course, add up to 1. And we pick the one that has the highest probability. So what we see here is, an expensive CNN might think something is a truck. That's its ranking 1, highest probability. But a cheap CNN might think it's a moving van or an airplane or whatever. But it might not think it's a truck as its highest rank. But, typically, so that's not accurate. But what we've seen is that the best result from the expensive CNN, right, is often within a top K of the cheap CNN. Like for instance here, it's within the top 3. If you take the top 3 of the cheap CNN, that mostly includes the expensive CNN's result. So what we do is the following. Instead of the earlier thing where we just created a simple index based on the cheap CNN, now we will create what is known as a top K index. So essentially the frames come in, we run the specialized CNN, and we essentially look for all the top K ranked results that are provided by the cheap CNN. So later on, when someone comes querying for a certain class, at that point, remember that by running the top K, right? Now we've included frames in the index that are moving vehicle, airplanes, everything. If I'm asking you for a truck now, you need to actually run it through an expensive CNN, which is fine. We can just run it through the expensive CNN, and then only present those results to the object, to the user. So for folks that are more familiar with machine learning, the left part of it, this is how we get the recall with the top K, and the right part of it, this is how we get high precision, which is to get rid of the junk that we threw into the index for the top K And why we threw in the junk is because we wanted a specialized, a compressed CNN, and why we wanted this is because we wanted the ingest cost to be low. Okay. So this specific thing on the right, that can be pretty expensive too, running these expensive CNN. Remember that here the user is waiting while you're running this expensive CNN. So how do we reduce that time? How do we reduce the latency? Approximate indexing means there's a non-trivial amount of work that's available at query time. So what we do is we can minimize the work at query time by clustering objects that are similar. These DNNs essentially, before they give off that probability list that I told you, right? They actually have something called a feature vector. So this feature vector allows, it's like a multi-dimensional vector. That is what eventually maps to the probability lists. And feature vectors are, in other prior work we've seen that they are great, sort of like predictors. Images with similar feature vectors are usually tend to be visually similar. Like for instance, all these three images, as you see example images, they have very similar feature vectors because they're visually the same. So what we basically do is cluster these objects, this top K index, based on these feature vectors. So, we had this figure, recall. So what we do here is basically not just put in the top K results, but also cluster them and put it. So essentially now while the amount of objects in the index is the same, they now fall into a far fewer number of clusters. And in these clusters, what we do at query time is, for every cluster, we don't run all the objects. We only take the centroid and we run it, and then apply that same result to everybody. So this removal of the junk, or the precision that I talked about in the right, now we've gotten to a point where that happens on a far fewer number of objects. And as a result, the amount of weight that the user has to do is significantly lower. A quick result highlight here, if you see, is, it's the same set of videos as before. Remember the same axes on query latency and ingest cost. Of course, these two are here. This is the query heavy and the ingest heavy baselines, and our work, which we call focus, ends up being significantly lower in its cost. Remember that we're talking about $380 per month per stream. We've got it down to single digits, and at the same time, the query is also much faster. Remember that on a month-long video, I said it takes 5 hours with the baseline. We take 2 minutes. So you can actually ask a question on a 5-hour video, and you'll get the result in 2 minutes. Let me show you a demo of how this thing works. I'll play this video. I hope this video plays. Okay, yeah. So yeah, hopefully that demo was clear and it showed the fact that you can, search for any kind of object you want in that list, and it's significantly faster. Yeah, so before I conclude, there are like a few other things, that work that we have going on that I did not really get a chance to talk about, but is there in our project webpage. On cross-camera video analytics, clearly many deployments don't have one camera stream, but they have multiple streams. And how do you do this cross-camera systems? Privacy is a huge thing with video analytics. So, how do you do private video analytics on the cloud or on the edge with what are called these enclaves, these compute enclaves? And finally, how do you train these models continuously on these edge devices? Because, the models are essentially trained upfront using some representative data then, but over time, as the scene changes, the model also, drifts away in its performance. Ongoing work, I encourage you to check all of these out. I also want to point out that we have actually released this code on GitHub. So at that URL below, you should be able to find the code, check it out, and you should be able to run it. I do encourage all of you, if you're interested, to actually give it a spin. Let us know if there is any questions, if something doesn't work, and so forth. More than happy to help get you all set up with it. So yeah, to conclude, I talked about the key three pieces around how do you run these live video analytics with approximation, and how do you use this results from these live videos to build an index that enables interactive query of the stored video data sets. So the URL on the left should provide you, it's the project webpage that provides you all the links to the details, the papers, everything in our project. Yep, with that, I conclude my talk. Thank you. I can take any questions now.
So questions are visible in the right side.
There's questions in the right side, right? Yeah. Right. So the first question is, how does the accuracy and efficiency change between cheap CNN and expensive CNN? Okay, so quite a bit, and this is very model dependent. Let me take efficiency first. Clearly, the cheap CNNs, right? I said the way they're taken is the fact that you take this big expensive DNN that has a lot of the layers, and a lot of the advancements that you see right now is because people just freely throw layers at it, neurons at it. And so the model becomes pretty bloated. So often, how cheap do you want the cheap CNN to be is depending on how many of those layers you want to strip out. You can even get a factor of, like, for instance, in the second part of the work around focus, right? When we use this cheap CNN for ingest, that cheap CNN was 100 times more efficient than the expensive CNN. For YOLO, which is the more popular object detector, its a tiny version is roughly, I think, about 8 to 10x cheaper than the expensive CNN. So it depends on the kind of DNN and how much you want to actually compress it. To the second point as to how the accuracy varies, it's a question that depends a lot on how this cheap CNN is trained. Right? Like, think about it like the fact that if I'm, it's like the amount of brain power that I'm giving to the DNN. So what happens when they say with cheap DNN is it is now trained not on the entire data set the original DNN was trained on, but on a much smaller data set. Right? When you train it on a much smaller data set, what happens is the fact that yeah, sure, for that specific data set it performs great, but then over time you have to constantly keep retraining, which is what I was saying about continuous training and data drift. But as long as you can ensure that the constant retraining happens, then accuracies, I would say, can be made comparable. But you need to make sure there is continuous retraining. Okay. The second question is, while implementing single shot methods like SSD and YOLO V3, we generally have trade-off between swiftness and accuracy. So could you state the state of the things? Could you state the things that need to be taken care of while choosing between SSD and YOLO V3 in different scenarios? So this is mostly all an empirical science. So, mostly there's no defined rules that we have to take care of in different scenarios. But a lot of this work is along the line where we just get to a point where we think about it, that we know from history that, hey, for this specific video, like I showed, for instance, for a busy intersection, YOLO V3 usually works well. So more or less try to go for it. It usually works well. Yeah, we've seen it. We've learned from history. Some other scenes we would see, like something like the SSD would work well. So we can go with it. But it's mostly like what you get out of historical observation. But it's also more robust because that's very data driven, and let's make sure that you're not too optimizing for something that is just based on a single heuristic or something like that. If that didn't answer the question, Nitin, I guess you posted the question. You or anyone who is has a follow up can feel free to speak up.
We can handle that in the launch, sir.
Okay,
sure there'll be.
Yeah, got it. Okay, what is the next question? Oh boy, wait, this got redefined in the. Okay, I'm just picking it as some random order, so apologies if your question didn't come up first. In future, processing will be done by cloud provider, or all it can be done offline in the camera hardware itself? Great question. Yes, in the future, processing will not be done all on the cloud, or at least I don't think, or we don't see it happening that way, because the amount of data that is produced, especially by videos, is so high that as you start putting them in a whole bunch of places like homes and even factory floors and so forth, there's not enough network uplink for it to go. And it's, even if you were to provision the uplink, it's a huge amount of waste, the amount of network uplink you provision. My hypothesis is, or my bet is, that a lot of the processing will happen in this hybrid scenario where closer to the camera streams or on the camera itself, there would be filters that you will put in, lightweight filters, an example of which you saw in the talk with this cascaded pipeline with background subtractors and so forth, which are more lightweight. And then the DNNs itself will be running a little bit away from the camera stream. But the amount of times you will have to go to the cloud and the amount of data that will reach the cloud will be very small. Okay. Is cost an issue at Microsoft? Meaning, do you have to think over $100 to train a huge model? The quick answer is no. I mean, Microsoft does not have to think about $100 to train a huge model. We often train models with tens of thousands of dollars. But the point is, if you're building a solution that has to run at scale, where it is, like, remember that our goal was actually democratizing video analytics. So if we have to do that, having a solution whose training cost and inference cost is very high does not work out. So cost is definitely an issue in the space around machine learning. And as it stands right now, a lot of the solutions, however, the cooler they are, the more expensive they are. So yes, grappling with cost to get the costs down, very much a focus. And if you do it, the machine learning folks would love you. The other question, is there a defined way to get the K in the K indexing? No, there isn't a defined way. And it's a very good question, because in general, right, with any K means, there's no defined way. It's mostly rule of thumb that people use in terms of how many K you want and so forth. But specifically from the point of view of what we our work was with the second part of the thing around interactive querying. Yeah, we usually stick to K that is roughly about 2 or 3 because of the fact that the more K that we put in, it more gets to a point where you have to do an enormous amount of work at query time to remove that, for precision. So to sort of like keep it somewhat balanced, we stick to a K of 2 or 3 in our experiments. But again, that's the rule of thumb. Another question from Vignesh. Can you share what is being done for low light images? Nothing specific, I would say. But what we do for low light images is the fact that by doing this periodic profiling, so to speak, right? What we end up doing is, for instance, with doing periodic profiling, we'll know that, hey, you know what? When the light is pretty low, don't downsize the frame too much. It's already a difficult job to find these objects. Give it more frames, so have a higher frame sampling. In terms of selecting the DNN, I told you that the cheap CNN can be specialized. Well, guess what? There are DNNs that are specialized for these low light images at night, images at dusk, whatever. Yeah. So then what happens with this profiling is that automatically these models that are specialized for certain times of the day suddenly start performing very well. So while we don't do anything explicitly, we do handle it in our deployments because we've been running this for months together. We handle it pretty well because it's a data-driven profiling approach that we take. What is the Vignesh's has a part 2 as well. Do we just use cameras with night vision and then switch models to run on the right vision data? Oh, great, exactly. Yeah, I guess part of it I agree. Yes, the second half of your question, which is what I just explained as well, I suppose. But do we use cameras with night vision? I mean, yes and no. Typically, this is a bit of a thing where the technology meets the economics, in that the more your cameras are just commodity, the better off it is. The more your cameras require sophistication, like depth and this and that, it slowly starts getting to a point where the cameras become expensive, and then the whole objective of democratizing, right, falls apart, because forget about democratizing the processing costs. The cameras themselves have become so expensive that what are you democratizing? So yeah, we have to be careful. I think night cameras are definitely a great idea, but at the same time, we have to be careful about the fact that we don't rely too much on the camera having too many smarts. Along the lines is the same answer, where you also want to make sure that the camera doesn't need to have too much compute on board. Because of the fact that if you add too much compute on board, then the camera again becomes very expensive. And so yeah, there is that balance in terms of how sophisticated you want your camera. Yeah. Okay. Another question from Nitin. Diversity of research areas at MSR India versus MSR USA. That's a good question. Yeah, a little bit of a history of background. I was at MSR India as a research fellow after I think I did my PS2 in MSR2, and then I spent some time in MSR India as a research fellow before I went for my PhD. So right from this time, I have seen the MSR India lab, starting up to now. There is not a big difference in the research areas. The focus areas in MSR India is more or less the same thing, with bunch around systems, networking, machine learning, security, complexity theory, algorithms, crypto. So not too much that I would call out is particularly different. There is one aspect of MSR India, though, I can recall is different than other labs, which is MSR India has this group called Technology for Emerging Markets. I don't know if they have a more updated name, but that was the name at least I remember. And that group focuses on producing technology that works in very constrained setups, like often that we might have in rural parts, which is that, hey, you can't expect 100% connectivity and all that, and we can't expect the connectivity is great. We can't expect that that we should expect that the hardware is probably more going to see many more faults because of dust and so forth. So they have some of those kind of constraints that they work with. So that aspect of MSR India is probably unique. But otherwise, the set of things that happen here in the US, more or less the same areas are the focus in India too. The last question: is government or corporates monitoring us at all the times? Oh boy, it's a sensitive question. No, the whole focus of our work with video analytics that I explained, and unfortunately I didn't have the time to go over the privacy aspects of it, though we've done a lot of work on it. The whole thing is to ensure that organizations don't have the ability to monitor us at all the times. We really want to be at a place where, with video analytics, there is a lot of benefits that you can get if we actually just do what we do, which is like, let me just detect what these people are, maybe alert them, it's safety and so forth. But we also want to make sure that specifically we are not getting in a big brother regime where we always being monitored. So Edge is very great from that point of view, because the Edge ensures that Edge is in your control. You can literally deploy an Edge box in your building and so forth. So which means that the video data can be programmed to never leave the building or the home, for instance, ever. Which means that sure, no one else is monitoring you. You are basically using it. It's being processed in your own home, and it's alerting you, and you're getting all the benefits without it, going out everywhere. So no, the answer is no. They're not monitoring us in all times, and we need to keep developing technologies that ensure that they cannot, and we need to make a very privacy first sort of a solution for video analytics. Yeah, I guess that's it, unless I missed something else in the other ones. There is one that said, how is the work process at MS Research? Work process is fairly, like independent. You can go ahead and you can go ahead and work on any area you want to work on, whatever is your research interest, and that need not be specifically databases or systems or machine learning. You can do anything that you want, and you go about working on it. Try to find the interesting problem, solve it, and we are encouraged to publish a lot as you go to our webpage as well for the video analytics webpage. We can definitely go ahead and you can see that there are a lot of papers that we write and there are a lot of external collaborations that we do. So doing external collaborations with universities, with students, that's great. I mean, I love doing that. A lot of my colleagues also love doing that, and that's how we go. Yeah. How can we contact you for any future doubt and guidance? You can just drop me a mail. My mail ID is fairly simple. It is the first two letters of my first name, ga@microsoft.com. So yeah, feel free to drop me a note if you have any questions, want to chat, want to discuss, brainstorm, anything. Yeah. Okay.
Thanks a lot, sir.
Cool. Thank you, everybody. Yeah. Thank you.
We know you have a very busy schedule, but it's great you delivered an hour-long lecture here. So now I think we can join the launch for anyone who wants to ask you questions one-on-one.
Yeah, I can stay on for like a couple more minutes easily. So yeah, cool. Thank you, everybody. Thanks for attending, and thanks for inviting me.
Thank you, sir.
Let me see, how do I get to the launch?
Sir, I will be ending the session now, and you can head over to any table.
Okay, I have to head to a table. I'm sorry, I'm not sure how do I head.